Hello, this is Aykut from Hacettepe University. So today we're gonna have this short lecture on economic growth again. This time we are going to work on a Schumpeterian model. Now we must be careful with the terminology here a little bit. The previous model that we studied in this lecture series, it was a product variety model. So in a larger sense of the term Schumpeterian, it was also a Schumpeterian model. Why? Because there was this sector, the research sector, that innovates new product varieties for profit motive. Okay? But in that model, there was no creative destruction. Okay? So in the Aghion and Howitt's text, the model that we study in this lecture is called Schumpeterian because there are both things. Okay, first profit motive, and then there's creative destruction because the new innovator basically replaces the old monopolist that produces the intermediate good. Okay, so this is a rather nuanced way of understanding what a Schumpeterian model is. And we will have two versions of this model. First, in this lecture, we're going to look at a one-sector version. In the next lecture, we will see a multi-sector version. But if we understand the one-sector model, understanding the multi-sector model is just very simple. And I should also emphasize that this is the textbook version. So it is much simpler than the model in the paper. The original paper is due to Philip Aghion and Peter Howitt, published in 1992 in Econometrica. Here in the simple version, we have the final good sector, and the final good is used for research. All right. So in the paper, you will see that labor is used for research input as research input. So there's this nuance. And also, the construction of equilibrium is a bit more complex in the paper, because in the paper the authors find the dynamic equilibrium through a perfect foresight equilibrium dynamics. So what will happen in the future will affect today's decisions in terms of research. But here we are gonna sterilize that, forward-looking aspect of the model by some assumptions. Okay. So let's start. So this is some fundamentals about the economy here we are studying. So time will be discrete. So this is different than the earlier product variety model that we studied. And here the length of a period is long. Okay, because we assume that people live just one period. So you may imagine that the length of a period is just one whole lifetime of a generation. Okay, and we assume that individuals are located within this interval. Okay, so this interval 0L basically is the set of individuals in this economy. All right, so in total, the measure is L. L is fixed and greater than 0. Also different from the product variety model, we simplify the preferences in this way. Okay, so here the agent's utility, the lifetime utility in this case, will depend on consumption, but it will be a linear function of consumption. All right, so in that sense, these individuals are risk neutral, and that could be any affine function that basically increases in consumption. Okay, so epsilon is greater than 0, but psi could be any real number. And we assume that every individual supplies labor to the labor market. Okay, so everybody works and they have this unit endowment of labor, so the total labor supply would be L as in the earlier models. Okay, so in this model there's again a final good sector, an intermediate input sector, and there's this innovation aspect. So let's look at the final good sector first. Now what you see here is a Kodak's production function, and the intermediate good x here is capital. So if you compare this with the product variety model, now we have only one intermediate good. All right, and we have L, and now the labor productivity which was equal to the number of machines in the product rate model, here is just denoted by AT, and this is the productivity. Okay, so here the assumption is that each each intermediate input, depending on the version of it, comes with a labor productivity term AT. Okay, so if you innovate in this model, you're basically coming up with the blueprint of a new version of an intermediate input that would imply a higher productivity level AT. Okay, so that's the idea. So innovation here is basically then the vertical innovation. All right, so we will have in the product right model, the innovation was horizontal. So it was basically the product innovation, right? New products are invented in that model. Now here we have the same task that basically completes, that basically appears in the final production function this way, but now it is attached with this productivity level 80. So if you innovate, you create a new version, a better quality version of it, or the higher productive version of it. Okay, so it's in the vertical dimension. So Y is output, which is typical. So X is the intermediate input or capital or machine, whatever you call it. So again, productivity, AT, is the productivity level associated with that version of the machine, which is used in period T. And L is the labor. Endowment of the column, or labor demand if you want to be more specific. So we assume once again that the final goods sector is competitive. So firms here are price takers, so they want to maximize their profits. So if you solve this, very simple problem, you may end up with these inverse demand function for X and inverse demand function for L. Okay, and so this part is pretty similar to the product variety model, because this is just inverse demand. And that inverse demand function is taken as given by the monopolist that produces X. Okay? So let's look at this monopoly problem. So the inverse demand for XT is there. Inverse demand times, this is price times the quantity is the total sales. And again, there is this one-to-one production technology that converts the final good into the intermediate input. Okay? So that production technology is the same. So then if you, again, solve this problem exactly as in the product variety model, you end up with this optimal level of intermediate input. Okay, so the local monopolist, the monopolist that produces this intermediate good at period T, has this optimal level of production. Okay, and what we see here is that it depends on the size of the labor force, because that basically creates the, that basically signifies the size of the final goods sector, which is, the sector that demands the intermediate good. And it also depends on productivity. So if the machine you are producing is more productive, you are producing, more of it. Why? Because again, the productivity of X depends positively on A. All right, so that's the idea. Okay, now we can start talking about innovation. Let me now share a couple of assumptions here, which is, somewhat implicit in the text. So, since this is a textbook, some of these assumptions are, given in, very quick way and without motivating the entire discussion about it. So let me help understanding that. So first of all, we assume that innovation is, innovation takes place at the beginning of period T. All right, so that's an important assumption. And we're going to assume that there will be only one individual that targets the innovation. So, okay, so there's this one entrepreneur that would try to come up with a better version of this XT. Okay, better version means higher productivity. And we also assume that innovation will be stochastic. Okay, so there is the success probability and there is this failure probability. And of course, success probability will depend on, what is the innovation input allocated to the, to the research. So that will be an important element, an important input, because if we spend more on innovation, we're going to increase our possibility of success, probability of success, okay? But let's look at the equation here. So AT is, again, the productivity term. That would be, prevailing at period T, right? So that productivity level could be two things. If innovation is successful, it will be equal to gamma times AT minus 1. Okay, so AT minus 1 is the level of productivity in period T minus 1, and gamma, which is greater than 1, is the step size. Okay, so what is happening here? If innovation is successful, AT will be greater than AT minus 1, so productivity will be larger. Okay, because I successfully, invent a better version of it, a high productive version of it, all right? A high productive version of the intermediate input X, okay? But if the innovation, effort is not successful, then productivity remains the same, okay? So there's no increase in product, so AT is equal to AT minus 1, okay? So then, now we may imagine, we look at this from the perspective of this prospective innovator, okay? Because that innovator will replace the monopoly of the previous period. If successful, he or she will replace that firm, and it destructs the monopoly rights of this earlier firm by creating a new version of it, right? So it is called creative destruction. This entire process is called creative destruction. So the targeted productivity by the innovator is then equal to gamma times AT minus 1. And it will be denoted by AT star just for the sake of notation, for notational convenience, okay? And as in the product rating model, we again use RT to denote the research expenditure, okay? So the research expenditure is once again is accounted in terms of the final good, all right? So final good is taken from the market and spent on innovation. Okay, so here is the probability of success. So this is a Greek letter mu. So mu t is the probability of success, and that probability of success depends on two things. First is the research expenditure, RT, and the other is the targeted productivity, AT star. So what's happening here? If RT is getting large, because we assume that this productivity, so this probability depends positively on R and negatively on AT star. So what's happening is that if I spend more on research, then my probability of success is getting larger. But if I am targeting a very large productivity level, AT star, then probability is getting lower. So this term here then reflects this fishing out effect, right? Or increasing complexity effect or something like that. So, it is also called low-hanging fruit, right? Because if you study innovation, if you're in the early stages, it is easier to collect, low-hanging fruits from the tree, right? But if you try to go further, it is harder to get the fruit from the higher stages. So or it is the fishing out effect. If there is this lake, I go fishing there. So since in the beginning it is the ideas are open there are many good ideas, so it is easier to catch good ideas, good fish first, but then the number of fish is getting lower as I continue, and then it is getting harder to innovate, all right, harder to get fish. So that's the idea, all right, and we denote this normalized research expenditure by N. Okay, so NT would be research expenditure, RT normalized by the targeted productivity level. Okay, so this is the specification of this function phi. So it depends positively on N again. Lambda is some positive number, and sigma is between 0 and 1. So here there is decreasing returns to scale in knowledge production function, okay? Because here, before creating knowledge, we first create the success probability, but that success probability, the marginal return in terms of N is, decreasing, okay? So that will be important. There are other versions of the Schumpeterian theory where there's no decreasing terms of scale, where there's a constant terms of scale, and we're going to see such slightly more complicated models as well. But for now, we are looking at a version where there's this decreasing terms of scale in the research technology. Okay. Now, of course, if the prospective innovator will replace the earlier monopoly there, then it is important how much to profit. All right. What will be the level of profit that I would make if I successfully invent a new version that will have the product level 80 star. Okay. So for this reason, we have to solve for the targeted profit as well, but we're going to do that in a moment. But the targeted profit is denoted by pi t star. Now, obviously, we want to calculate expected profit to just find what is the optimal level of R to be spent on research, right? So now this is an expected payoff problem. We must be careful with the hidden assumptions there. So first of all, minus RT will be the cost, regardless of the outcome, right? So I could be successful, I could be unsuccessful, but in both cases, I will spend R into research. Okay, so that's the cost part. Now the profit part is there. Okay, so if I be successful, then I will get the targeted profit level, pi t star. So mu t times pi t star is that. And if I'm unsuccessful, I will get nothing, because either the same product, so the same monopoly will be producing there, or that monopoly rights will be transferred to some other agent, but the same, 80-1 level of productivity machine will be used. All right. So I will get nothing if I am unsuccessful, and I get pi t star if I'm successful. So this part becomes the expected profit. Okay, so this is expected return. All right, and this is the cost. So the expected profit is equal to that. Now here there's one assumption as well, which is important. As you see, if you compare this with the product variety model, in that model, we assume that once the new product variety is invented, that inventor will always produce it from that point of invention until infinity, right? For this reason, we calculated the present value of all future profit streams. Okay, now we are just assuming that that monopoly right is obtained for only one period. Okay, hence the profit is only obtained at period t by this prospective innovator. Why is that the case? Well, there are a couple of reasons. It is not totally unrealistic. Why? Because here the length of a period is long and one lifetime. So you may imagine that the patent law is such that so you produce that in that period, in that long cycle of time. Then after that, you die, right? You leave the stage as the monopoly, and the monopoly rights are transferred to either one other agent that will use the same level of productivity that you invented in period t, or it will be transferred. So it will be transferred to some other successful innovator in t plus 1. Okay, so that's the idea. That's the simplifying part. Again, in the paper, it is not that simplified because there is this forward-looking aspect of research behavior. But for our purposes here, this suffices to create enough content, sufficient content for us to proceed. All right. So once again, this is the expected profit of the prospective innovator that would either produce the new version of it or lead the stage as the unsuccessful entrepreneur. Okay. So, all right, let's calculate this targeted profit. Okay. Now, if you go back to the monopolist problem, remember that we already found the optimal level of xt. If you put this xt back to this profit function, you get this result. Okay? So not just xt itself, but profit itself is proportional to productivity times labor. All right? So that's key. And there's this parameter pi, which depends on alpha. So if you do the math, you will realize that. You will realize this. So if this is the profit level that would be obtained by the monopoly that produces a machine with productivity level AT. And if this is the targeted productivity level by the innovator, AT star, then pi t star would be written simply in this way, right? That's it. So then if we put all these things together, first we write the problem in this way, right? Because remember that there is 0 here, so this term basically cancels out. There's minus RT. And if I replace mu t and pi t star, I get this first. Now, to simplify the solution of the problem and to express everything in terms of the normalized research expenditure, I divide the entire expected profit by AT star, okay? So from this line to this line, I divide this term and this term by AT star. Why is that legitimate? Because AT star is a positive number, so it doesn't really change the solution, right? So then the problem is expressed in this way. And this is a very simple maximization problem. So maximizing this with respect to NT gives us this first order condition. And again, of course, we're assuming that the solution is interior, okay, because otherwise there's no innovation. So it is not really interesting. But then, as you see, this equation solves n, right? And here is the solution. So normalized research expenditure now depends on a couple of things. Sigma and lambda are technology parameters for the research technology. Pi, which depends on alpha, as you know, depends on the final good production technology. And L is the labor endowment of the economy. Now, since, of course, you should be careful that this is normalized, AT star will not appear here, right? Because now NT is just equal to, as you see here, NT times AT is the total research expenditure, okay? So, if you put this back into phi, you get mu, all right? And here's an important result. Since labor is constant, and since other parameters are also assumed to be constants, then mu t is equal to mu for all t. All right? So as long as the labor endowment of this economy is fixed, and as long as the research productivity and other technological parameters are fixed, then the success probability is always fixed. So it doesn't change from period t to period t plus 1. Okay? So that will be important because it will be, you will see that the expected growth rate will be fixed under this assumption. Okay, now let's try to understand growth of AT. First of all, let's go back to the very beginning, to here, okay? Now from this equation, you realize that AT is the main parameter that will explain the growth of GDP per capita, all right? So that's it. So as in the previous model of product variety, we are again interested in this term that appears on the front of labor. So it is the labor augmenting term in terms of productivity. So we are interested in the growth rate of this variable. And that growth rate is defined in this way now, because now, again, you should be careful. So innovation is taking place in the beginning of period t, so the growth rate that we are interested in, gt, is written in this way, all right? AT minus AT minus 1, AT minus AT minus 1 divided by AT minus 1. All right, so one important remark here is that gt is stochastic. What do I mean by that? Well, for some periods, since there's only one innovator, that innovator either will be successful or unsuccessful. So if the innovator is successful, which is a probabilistic event, then growth will be larger, right? Growth will be positive. But if the innovator is unsuccessful, which is also another, it also depends on the, probability 1 minus mu, then growth rate is 0. Okay? So here, growth rate itself will fluctuate according to the realization of the innovation event. All right? So yes, there will be this fixed probability mu, but this is still, not the outcome, right? Outcome could be either successful or unsuccessful. Okay? So for this reason, the thing that we are interested in is the expected growth rate. Okay, because what we know is that growth is either gamma minus 1, as you see here, or 0, right? But if we are interested in if we solve for the expected growth rate, then we can understand the very long run behavior of productivity and GDP per capita. Okay, so for this reason, we use again the expected value definition of the expected value to write this expected growth rate. So if innovation is successful with probability mu t, the growth rate is equal to this, because AT will be equal to gamma AT minus 1, right? So make the connection. And if innovation is unsuccessful, AT will be equal to AT minus 1, so this term will be 0, so growth rate will be 0, and this term will disappear. Okay? Okay, so there is this typo here, so this will be AT minus 1, all right? So be careful there. Okay, so there's this little typo there. Okay, so this is AT minus 1, all right? Be careful. Okay, so, and of course, as you see, if this is AT minus 1 as well, the AT minus 1 terms cancel out, so the expected growth rate is just equal to mu times gamma minus 1, all right? If you go back there, it's very simple math. So then you, of course, replace mu. Yeah, okay, so this is mu, again, another typo here, so there's this gamma minus 1 term here and gamma minus 1 term here, all right? Be careful there. Okay. For some reason, I have typos in this lecture. All right. So, okay, so this is mu, right? As we did earlier. So this is mu. Then there's gamma minus 1 term here and gamma minus 1 term here. And you see the graph here, right? So time t is now located in the horizontal axis. GT is on the vertical axis. So in some periods it is 0. In some periods it is gamma minus 1. So the expected growth rate is mu times gamma minus 1. Okay, so that's the idea. That's the simplest possible way to explain Aghion and Howitt's Schumpeterian model of creative destruction. Okay, this is the one sector version, so it is not realistic from many aspects, but it tells the heart of the story. Okay, so there is this initial monopolist that produces a given version of the intermediate input, but then there is also this prospective entrepreneur or the prospective innovator who basically tries to invent a better version of it. Better version means high productivity version. So then, of course, this high productivity version replaces the earlier version. Okay, for this reason, the successful innovator basically destructs the monopolies, the monopoly rents, monopoly profits of the earlier monopoly that produces the earlier version of the intermediate input. Okay, and if we solve this model, we find the growth rate in this way. So again, there's this gamma minus 1 term here and gamma minus 1 term here. But again, the growth rate depends on a couple of things. Here, pure technology. Why? Because preferences does not imply much here, because preferences are just almost trivial. Okay. So that's it. Now, one important extension will be, of course, understanding the similar mechanisms when we have more than one sector. Okay, when we have more than one intermediate input, and that will be an important extension, and we're going to study that in part 2. Thanks for watching.